Welcome back. Now we know how to expose variables to Blueprint. We've exposed these three, but we can also expose functions as well. Now let's take a look at what we're doing with the sine function. We're using the sine function, but we're actually transforming it by multiplying it by amplitude and multiplying running time by some time constant. Now, these are known as sine transformations. This is actually a version of the sine function that we say has been transformed. Now, let's say that we have a game designer who knows blueprints but doesn't really mess with C++. But this is a really nice feature and you'd like them to use their creativity in the game and see if they can find another application for it. Well, we can make this a function and expose it to blueprints. So I'm going to go to item.h and declare a new function. Let's make this a protected function. We'll add it right here in the protected section. Now, if you're wondering where you should place the function, whether it's public, protected, or private, just ask yourself this. Are we going to plan on calling this function from outside the class? For example, might there be an object out in the world that may have access to this item object and maybe call the function? Well, in that case, you would make the function public. But if that's not the case, it doesn't really need to be public. It could be protected or private. Now, the next question to ask is, do you ever see yourself potentially calling this function in a child class derived from a item? For example, we may specialize item by deriving a new class called, say, weapon. And if you think weapon might need to be calling this function, well, you can make it protected. And if you know for sure that this class will be the only class that needs to call this function, you can make it private. I tend to put most functions in the protected section if I'm not sure, but I typically move them out of one section and into another if the need arises. So you can always change where the function is and its access level later on based on your needs. So I'm going to make this function right here in the protected section, and it's going to return a float. And this function is going to perform the sine calculation, this equation here that we created. It's going to perform this calculation and return a float. And this calculation, as we mentioned, is the transformed sine function. So I'm going to call this function transformed sine. Now, the sine function is mathematically pretty versatile. It doesn't have to operate on a running time specifically. So our function could take a float as an input parameter, and we can simply call this value. So our transformed sine function will operate on this value. Now we can define this function, and a shortcut in Visual Studio is to simply hover over the undefined function and let this screwdriver pop up, which has a drop-down, and if we click that, we can create a definition of transformed sine in item.cpp. So I'm going to click that, and I have a little mini window showing me a peek into item.cpp, and this is the default function definition that it gave for me. I'm going to go ahead and dock that up here and come back and take a look. Now, notice a couple things. First of all, the function is fully qualified with the class name. That's very important. This is a member function. We declared it inside the class, and if we're defining it outside the class, we need to fully qualify the name using the scope resolution operator. And notice another thing, it has a default return statement. That's because this function returns a float, and when Visual Studio creates the automatic definition for us, it doesn't know what we want to return, but it has to return something, so it just returns 0. Well, what we're going to return is the result of our transformed sine calculation. So we're going to copy this, and up here in transformed sine, rather than returning 0, we're going to return this expression here. And we're taking a value as input. So we don't need to just get the running time member variable. We can use value instead. And that way, whoever's calling this function can simply pass in whatever they want the sine function to operate on. Okay, so far so good. We have a new function. But we need to expose this to Blueprint because we have that theoretical game designer who may have a use for this. So to expose a function to Blueprint, we use uFunction. So it's kind of like uProperty, only it's uFunction. Now notice the VA args there. Remember that means variable number of arguments? We can have multiple arguments in this, just like we can in uProperty. Well, for uFunction, we're going to add a uFunction specifier, and that specifier is Blueprint callable. And it does what it sounds like. It makes this function callable in Blueprint. Now, before we compile, I'm going to go back down into tick. And instead of doing everything here in the tick function, what I'd like to do is comment out the line here where we're calling add actor world offset. And I'm going to comment out this line as well. So all we're doing now in tick is updating running time. Let's go ahead and save and hop back into the editor and hot reload. All right, so we're done hot reloading. Now we have this transformed sine function. If we right-click in the event graph and search for transformed, there's our transformed sine function. And if we click it, check this out. We now have a new custom Blueprint node. Awesome. Now we can take our running time and plug it on in. And if we go ahead and hook that up, we now have this function being called every frame. Now, the transform sine function, if we go back and look at it, here it is. It doesn't actually change our actor's world location. It just calculates a float value and returns it. But here in the editor, we can take that return value and use it. So let's drag off of transformed sine and use add actor world offset. And we can choose to use this any way that we want. So let's say that we'd like to add an offset to the actor's X location. So we can right-click on this, delta location, split the struct pin, and plug the return value from transformed sine into the X. So let's compile and hit play. Now take a look. Instead of going up and down, it's moving back and forth in the X direction. So now we found a new use for transformed sine. Now let's say later on we decide, well, transformed sine doesn't really need an input parameter. We're always just using running time. There's no other use for it. And you may have noticed that some Blueprint nodes don't actually have an input execution pin. For example, if we call getActorLocation, notice that this Blueprint function does not have an input or an output execution pin. It simply has an output value. This is known as a Blueprint Pure function. And Blueprint Pure functions do not change anything. They just calculate a value and return it. Well, transformed sine just calculates a value and returns it. So this could be a Blueprint Pure function as well. I'm going to go ahead and select it and delete it and head back into Visual Studio. And in item.h, instead of Blueprint Callable, let's make this Blueprint Pure. The specifier for that is Blueprint Pure. That's the nice thing about these specifiers. They're pretty self-explanatory. I'm going to go ahead and hit Save, come back into the editor and hot reload. Now that we're done, if we go back into Item and search for transformed sine, notice that the F is green now. That's because it's now Blueprint Pure. And if we click it, take a look. It's a lot smaller. Now it still has an input parameter which we could plug in, but it doesn't have input execution pins. That's okay because it's Blueprint Pure. I'm going to go ahead and delete getActorLocation. Now we have this transformed sine, right? And I mentioned that we don't really need to pass any value in anymore. So I'm going to go ahead and remove that and delete running time. And back here in Visual Studio, we can simply remove this input parameter since we don't want to use anything but running time. So instead of value here, we'll just use running time and we have our function. Now let's say your game designer says, this transform sine function is really great. Could you do one for cosine? And you're like, why would you want cosine? It basically does the same thing. And then they would say, no, it doesn't. Remember back in that video, when you drew the sine and cosine functions on the whiteboard, the sine and cosine are shifted by a little bit. I want to use that. And so you say, okay, sure. And you create a transformed cosine. So we'll go ahead and do that. We'll make a float returning function called transformed cosine. And you know that this isn't going to change any properties on the class, so we're going to make it a blueprint pure function. And we'll let Visual Studio give us a default definition for it. And we can basically copy what we did in transformed sine and paste it there. The only difference is we want to use cosine instead of sine. Well, the fmath function for cosine is simply cos, C-O-S. So since we just used sin for transformed sine, we could easily call this function transformed cos, like this. So I leave it up to you. It's really preference what you call this, but we'll call it transformed cos. Okay, so we now have a cosine. Let's go ahead and save all because we changed both of these files. And back here in the editor, we're going to hit hot reload. Okay, so we finished that. We go back into item. And at this point, you say to your designer, okay, let's see what you had in mind because I'm a little skeptical. I think what you're going to do is the same as the sine function. And your designer says, no, check this out. I'm going to take this transformed cosine function and I'm going to take transformed sine and plug it into delta location x. And I'm going to take transformed cosine and plug it into delta location y. Now check this out. And you say, okay, well, let's see what you mean. And you hook up event tick to add actor world offset, press play. And look at that. These things are moving in a circle. And this is because the sine and cosine functions, even though they're almost the same, they're not quite the same. They're offset, right? So one of the functions moves the object back and forth in the x, and the other moves it back and forth in the y. And because they both have the same amplitude and the same time constant, we're moving by the same amount in x and y. And this results in circular movement. Kind of cool, right? These kind of look like spoons stirring in a bucket of something. I don't know, but either case, it's kind of cool. So that is a reason why you may want to expose some mathematical function to Blueprint because either you or someone else on your team may have a use for it in Blueprint. So in summary, we've learned how to make a function Blueprint callable. And Blueprint callable makes a blue function with a blue F. It has an input execution pin and an output execution pin. But we also learned that functions can be blueprint pure, which means that they don't actually change any properties of the actor. In other words, we couldn't call add actor world offset in a blueprint pure function, but we can retrieve values out of the class and perform calculations and return values. And of course, blueprint pure functions can take input data as well. That's what blueprint pure functions are good for. So now we know how to expose functions to Blueprint, which is a very useful ability indeed. Great job. I'll see you soon.